Hello, I'm Hisok Jung from Hanyang University, and in this video, I'm gonna present our work Zero-Shot Compositional Video Learning with Coding Rate Reduction, which is published in ICCV 2025. Our research question is whether VLMs can generalize to unseen problems by composing previously learned concepts. In this simple motivating example, even the most powerful VLMs like ChatGPT cannot answer the problem by combining given knowledge of in-context examples presented in the left. Therefore, the training of VLMs relies on the massive amount of training data and huge model capacity to cover the vast diversity of real-world scenarios. However, the way humans learn new problems or concepts can be clearly explained based on the compositional learning as suggested in many cognitive science studies. The main focus of our work is compositional zero-shot learning problem, especially for the video understanding. As illustrated in the slide, in this problem, the action label of video is defined as a composition of spatial and temporal primitive categories such as sphere, cube, slide, and pick place, and the model only experiences videos having subset of action labels during training. Then, it is required to predict for videos having unseen labels like cube slide or sphere pick place by combining learned spatial and temporal primitive concepts. Now, I'm gonna introduce the main concept of our approach for the CGSL problem. Learning disentangled representations of primitive concepts is one of the most fundamental problems in CGSL, so we present a principled approach grounded in information theory by formulating a disentangled representation learning as a maximization of coding rate reduction. These disentangled representations can be recombined to predict for action classes, which are composition of spatial and temporal primitive categories. Before starting to detail the proposed method, I want to introduce some preliminaries of information theory to make further discussion clear. From rate distortion theory, the coding rate measures the number of binary bits required to reconstruct data within a specified decoding error epsilon, so it can be viewed as the volume of space spanned by data. Equations in the top row denote the approximation of coding rate for given a finite set of data vectors G, and R to the C of G is the sum of coding rate of subspaces partitioned by membership matrix pi. Then by maximizing the coding rate reduction, R of G minus R to the C of G, the learned representations become highly compressed in the same subspace while being incoherent between different subspaces, so the disentanglement across different subspaces can be derived. This optimization of coding rate reduction can be simply implemented by a gradient ascent method with non-closed form of its derivative. We implemented the iterative gradient ascent optimization of coding rate reduction in unrolled forward layers of the resampler-based model architecture. The input feature maps from the backbone video encoder is fed into the resampler module, and each block performs standard cross-attention along with a single gradient ascent update to the learned latent queries. By introducing cross-attention based architecture and learned latent queries, we significantly reduce the prohibitive computational cost of computing the gradient of coding rate reduction for large input feature maps. The disentangled representations are then passed through divided branches to predict logits for primitive spatial and temporal categories, and the compositional action labels are computed by multiplying these two logits, assuming conditional independence between them. The overall model is trained with 3 cross-entropy loss terms for spatial, temporal, and composite action labels, respectively. For experiments, We evaluated the proposed method on 3 challenging benchmarks, including zero-shot compositional action recognition and visual question answering, where it outperforms strong baselines and even large VLMs such as Inton VL2 and QN2 VL. We also evaluated characteristics of the learned representations with principal component analysis. By setting 2 distinct primitive categories for both spatial and temporal dimensions, we collected intermediate representations from videos corresponding to the 4 possible action labels. As shown in this PCA result of these representations, optimization of the coding rate reduction drives subspaces to be closely aligned with underlying semantic axis. In summary, our main contributions are straightforward. We propose an information theoretic approach for video representation learning by disentangling spatio-temporal information into multiple subspaces, and it shows a state-of-the-art performance on 3 challenging zero-shot compositional learning benchmarks. We also discovered the interpretability of the proposed method by rigorous qualitative analysis. This is the end of the presentation, and thank you for listening. If you have any questions, feel free to reach out by these addresses.